Now, if you allow me, the next speaker is Dr. Kelso of SelectTrack. He's an operator of SelectTrack, the world's first source of orbital element sets and related software and educational materials. Ladies and gentlemen, help me welcome Dr. Kelso. Do we have Dr. Kelso online? No? We're still having a little bit of technical difficulty. Please just hang with me a little longer. This is one of the challenges of, oh, there he is. Dr. Kelso, welcome. Sorry about the small delays. We're dealing with international conferences and 5-hour differences and all the technical issues that come with that. But thanks again, Dr. Kelso. Please, the floor is yours.
Okay, so I assume you can hear me?
Yes, please, go ahead.
All right, so I'm going to go ahead and jump into this. Seems like we have a little bit of a lag on the connection, but hopefully everything will work out okay. So I want to take my time today just to talk to you about some of the issues with trying to actually predict satellite reentries. And I think it's important, for this topic, since we're talking about, how things like re-entering debris might interface with air traffic, that we understand that there's some pretty substantial challenges to how we actually predict when that might occur. And so I'm going to go through a couple things. I'm going to look at our primary motivation for why this is an important issue and why it's going to become probably an increasingly important issue. We'll talk about some of the definitions to make sure that we're all coming at this from the same perspective. And then I'll get into some of the challenges of the physics in trying to do these types of predictions, because in most cases, we're going to find out that we don't really know when an object is going to re-enter, and that causes some pretty significant challenges. And then we'll look at a couple of examples for both controlled and uncontrolled reentry to try to give you some perspective on how that works. So, of course, I think most of you understand that the number of satellites in Earth orbit has been increasing since the beginning of the space age. What you may not realize is that it's been increasing rapidly just in the past couple of years. And so if we look at the time from the beginning of 2020, we can see that SpaceX alone has launched over 1,600 satellites. And to put that in perspective, that's an increase in the number of operational satellites in orbit by about 50% just one year. And so we're seeing that operators like SpaceX and OneWeb and several others are looking at not launching thousands of satellites, but they actually have licenses for tens of thousands of satellites that they're talking about putting into orbit. And so, the challenge becomes that, first, when you put a satellite up in orbit, I think some people might think that, once you put it up there at some point, the mission will end and the satellite will come down, and that's not necessarily the case. There are some orbits that occurs in, but for the most part, if they're above about 700 kilometers, they're not going to come down unless the operator does something to try to take them down. And of course, the problem there is that if you leave these thousands or tens of thousands of new satellites up in orbit, that increases the risk of on-orbit collisions. And so there's an increasing pressure to remove those objects from orbit as soon as they've completed their purpose. And to do that requires obviously re-entering through the Earth's atmosphere where they can threaten aircraft and as well as people on the surface. So, here's a quick graph that shows what we're looking at in terms of growth for the satellite catalog over the past 70 years. And you can see, we're primarily interested in the blue line right now, which is the number of objects that have been cataloged. And you can see a fairly steady growth in that up until about 2007. And then you start seeing these bumps in the number of objects that have been cataloged. And the first one occurred in January of 2007 when the Chinese conducted an on-orbit ASAT test that produced thousands of pieces of debris. The second one occurred in February of 2009 when the Iridium 33 and Cosmos 2251 satellites collided on orbit and again produced another couple thousand pieces of debris. And the increase is kind of slow because it takes time to actually catalog them. But as you go toward about 2020, what you can see is that the period before that, going from 2015 to 2020, we increased the catalog by about 5,000 objects. We've almost done that in the past year and a half. And so we're almost to the point right now where we have 50,000 objects. And so if you look at the red line, the decayed line, you can see that the natural decay rate has not changed significantly, but the green line, the number of objects that remain on orbit, is starting to grow pretty quickly. And so that's part of our concern for the motivation. So let's talk briefly about the definitions for the different types of reentry. So we do have, and we may see with the increase in things like tourist flights into orbit, right now, those seem to be suborbital, but we do see that there are a very small number of reentries that are considered a targeted recovery. So we have maybe a cargo ship like the Crew Dragon coming back where they want to recover the cargo, or you have human crew on board that obviously you want to recover safely. And those are reasonably well understood, assuming that the reentry occurs as expected. It's not really much of a risk. There are issues with things like delays that might occur with weather on the ground that could change the recovery area that would affect air transportation. The next category would be what we consider controlled reentries. And those are typically targeted for something that's referred to as the South Pacific Ocean uninhabited area. And I'll show you that on a graphic here in just a minute, but it's an area in the South Pacific where there are actually no human residents. And so that doesn't mean you can't have ships or airplanes flying through there, but it's a reasonably safe place to put things, and things like the Mir space station from 2001 were actually deorbited there. And then we have semi-controlled. We're not going to really spend a lot of time on that, but that involves trying to get the satellite down to a point where it's going to reenter, but not being able to actually drive it into the atmosphere so that you have good accuracy on when that might happen. And those typically happen within one orbit. And you may be able to realize that one orbit around the Earth is, about 40,000 kilometers. So that's a pretty long ground track that you might have to worry about some kind of an interface with air traffic. And then the one that I think we're going to be most concerned about are the uncontrolled types of reentries, where it's all being done by natural forces, and those natural forces have lots of uncertainty. So here's a map of the world. It shows specifically the South Pacific uninhabited area there. You can see it's a fairly large body of water where there are no islands or other places where humans would live. And so that's what we're going to use for the controlled reentries. And that doesn't mean that you can't have them outside of that area, but it does kind of minimize the chance of interaction. Now, if you're traveling between, say, New Zealand and Chile, that could be a problem, but for the most part, NOTAM should take care of that kind of stuff. So what are some of the challenges that we face in trying to do predictions, whether they're for controlled or uncontrolled reentry? Well, the first one is obviously we're going from the near vacuum of low Earth orbit down into the atmosphere, and predicting both the conditions in orbital space, in other words, above what we would consider to be the Earth's atmosphere. There are still forces that affect drag on the satellites, and those are driven by the interactions with radiation from the sun and the geomagnetic field of the Earth. So the sun goes through, phases where the activity can increase and decrease. When it increases, it generates more heat that gets absorbed by the atmosphere, that expands the atmosphere and changes the drag characteristics for the satellites. And similarly, for the geomagnetic fluctuations, the interaction with the part of the charged particles that come from the sun are going to be strongly influenced by those geomagnetic fluctuations. And we don't really have a very good ability, despite decades of trying to predict these things, to do that very well, even just a day or so ahead of time. And so trying to predict with any degree of certainty when something's going to come down from natural effects is going to be difficult. And it also affects when we're doing controlled reentries. Of course, one of the issues that we have, whether you have a controlled or uncontrolled reentry, is that as the spacecraft, which is designed to be light and to operate in a vacuum, will start experiencing high acceleration or deceleration as it interacts with the atmosphere. And so as that happens, that can cause breakup of the satellite. It can change the attitude, which changes the drag characteristics and causes not only a difficulty in trying to predict where and when it's going to come down, but of course it produces lots of other debris that spreads out and increases the area that we're going to be interacting with. And the result is for these uncontrolled types of reentry that the predictions can have uncertainties of 10 to 20% or more. So if you're looking a day ahead, trying to predict when something might reenter, you could be talking anywhere from a couple of hours to 5, 6 hours uncertainty of knowing just when that's going to come down. And again, if you think about satellites in low Earth orbit that have about a 90-minute orbital period, that's several orbits around the Earth that you don't know when the satellite might come down. And we'll talk a little bit about how that plays out here in the example towards the end of this presentation. So let's start with the controlled reentry. This seems to be, a fairly easy one to deal with, but of course there's a lot of requirements to be able to do controlled reentry. And so the first thing that has to happen is you have to have a satellite that's still active. And, in a lot of cases, we find that satellite operators want to get the most out of their satellite, whether that's for scientific or commercial use, and they will tend to push the use of the satellite right up to the end. And that may mean that the satellite dies unexpectedly, which means it can't be controlled, or we can get into a situation where the satellite fuel reserves have been overestimated and there's actually not enough fuel to achieve a controlled reentry. So we've got to have an active satellite, got to be able to command and control that satellite, got to be able to control the attitude of the satellite as it enters the atmosphere. And before some of those stronger atmospheric effects, the deceleration and everything, start making control of the satellite impossible. And of course, one of the issues that we see is that not all active spacecraft are maneuverable. So we have smaller satellites, typically CubeSats, don't have maneuverability, but even satellites like the SpaceX Starlink satellites that are larger, while they are maneuverable, they use ion propulsion, which doesn't necessarily give you the kind of ability to predict with great accuracy when those are going to come down. So there's a lot of requirements to be able to make that work, and we don't see that in all cases. And so, we had a good example of how that kind of thing could play out back in 2008 when the European Space Agency undocked their ATV-1, the Jules Verne, from the International Space Station and targeted a reentry over the South Pacific. And so you can see on the left a picture of what the satellite looked like as it was undocked from the ISS. You can see the main body and the solar panels. And then you can see a picture that was taken from one of the aircraft that was monitoring the reentry from the reentry area. And you can see what the result of going through those decelerations and the atmospheric heating does to the satellite. It generates hundreds or thousands of pieces of debris. It's difficult to model, which pieces will break off when. And as you can imagine, the area that this is going to come down over is going to span many, many kilometers on the surface. And so if you had an aircraft coming down, you'd have a reasonably good idea of when this was going to happen and where, but not to the degree of knowing that a specific piece is going to hit an airplane if it were operating in that area. So even on the controlled reentry, there's a lot of uncertainty involved in that prediction. And so as long as you can put in an area that you can block off from aircraft and ships, it seems to be a reasonably minimal effect on what the interface is with the air traffic system. But, one of the things that you can see, and this is, another one of the controlled reentries that was done back in 2001, where the Russian space station Mir was deorbited. And you can see, some pictures as it was going through the process of decaying from orbit. You can see the effects of the heating and the accelerations on just the solar panels for that object before it got to the point where it was actually physically breaking up in orbit. So you could see how things like solar panels might break off, before the major reentry and have secondary types of reentry associated with that particular object. And so it makes for a very challenging case, even in controlled reentries, to try to predict exactly when these things are going to come down. So for uncontrolled reentry, what are we talking about? Well, the overwhelming number of objects in Earth orbit are uncontrolled. So right now, we have just over 4,700 active satellites in orbit. As we just mentioned, not all of those active satellites are maneuverable to be able to achieve some kind of a controlled reentry. So for the overwhelming majority of those satellites, those reentries, if there's going to be one, is going to be uncontrolled. Of course, it turns out that we're not doing a very good job of maintaining the environment up there. So not only do we leave things like the active satellites, or do have the things like active satellites up there, but we still have almost 2,800 dead satellites that are up in an Earth orbit. Not all of these are in low Earth orbit, so some of them are in higher orbits, but just the same. And we have 2,000 rocket bodies used to put those up there, still up there in orbit, plus another over 12,000 pieces of debris that are large enough to be tracked. That's out of a population of about 2,200 objects as of today. So, any of those objects that are in low Earth orbit could re-enter at some point in time. And it's a question of trying to figure out, to be sure, one, that you're tracking the orbits well enough, and then doing the predictions to try to get a sense for whether they're going to re-enter at a particular time, and then trying to do an assessment of whether any of the spacecraft or debris would actually survive re-entry to get to the surface. But as you can see in the picture on the right, things like pressurized vessels for gases or maneuverable fuel can actually survive re-entry. And you can imagine that something that size hitting an airplane would not produce a good effect. So there's a lot of threat there, and there's a lot of objects that could be in that uncontrolled reentry case. So I want to look at one example that I think most of you are probably familiar with. Back in May of this year, there was a lot of press about the Long March 5B rocket body that was used to launch the Chinese space station back at the end of April, re-entering into Earth orbit. And of course, one of the reasons that there was so much press about it was that the estimated mass of that rocket body was about 21 metric tons. So not a small object. In fact, it was the sixth largest object ever to re-enter from Earth orbit. And for most of these, now this isn't necessarily specific to this particular rocket body, but for rocket bodies in general, it's estimated that anywhere from 20 to 40% of the mass could reach the Earth's surface. So that's a pretty substantial risk if it were to actually hit anybody or anything on the surface or near the surface. And so what I want to do is I want to take that example and talk about some of the different ways that we try to estimate where those reentries are, because as it turned out at the time of the event, there was a lot of uncertainty about where it was going to reenter. And some of it was just because we weren't really using the proper techniques to do that modeling. And I think there was a lot of general misunderstanding in the public. And obviously, we want to make sure that, as we go forward for trying to figure out how we would deal with this type of interaction, with the airspace, we want to make sure that we're doing that from the perspective of having the best information possible. So here's the ground track for the Long March 5B as it was coming up on the time of reentry. This is a graphic produced by AEROSPACE. And so you can see the ground track over a good part of the day. And, the satellite was in an orbit that was inclined 41.5 degrees, which meant that it passed over the Earth's surface anywhere from 41.5 degrees north latitude to 41.5 degrees south latitude. And you heard a lot of people saying, well, it could re-enter anywhere in that area. And that's actually not a very good way to describe the possibility of re-entry. In fact, you can see that Portugal and Spain, and then most of the United States are all under that area. But even if the satellite were going to re-enter anywhere along those ground tracks, it's only on that very slender line where the ground track is, and there are large gaps in between each orbit as the Earth rotates underneath it. And so it's not like it can re-enter anywhere. It could re-enter potentially anywhere along those tracks. But as we'll see in a minute, there's actually reasonably easy ways to refine those estimates. It doesn't produce perfect results, but it does give us a good estimate of where it's going to go. So if we get down to the point where, and this is again from the Aerospace Corporation, we get down to the point where we're coming up on where the reentry is expected to occur. You can see up in the upper right, there's an estimate that was produced at 2034 on May 8th for reentry about 7 hours later, and it has an uncertainty of plus or minus 2 hours. So that's not a particularly good estimate when you're thinking about 4 hours being almost 3 revs around the Earth. It gives you a lot of potential places where it could come down. But you can see that we've already reduced the possible areas where a reentry could occur pretty significantly. And you can see that for the most part, over the land masses affected, you still have the possibility that it would come down over, say, Portugal or Spain, or it would come down over the southeastern United States, or maybe even come down over parts of the Middle East or Australia. And so there's still quite a bit of uncertainty involved in that. So what we did so I operate Celestrak, and the idea for Celestrak is to be able to put out information that helps inform the public on how to better understand these kinds of events and all sorts of things that have to do with space situation awareness. And so, the reality is that the satellite is not going to re-enter at any point in its orbit. It's going to re-enter at the lowest point in its orbit. Now, in some cases, the orbit is fairly circular and that can spread out. But what we did on the graphic on Celestrak was we said, well, we're going to show, the areas below 150 kilometers in yellow, and then anything that's below 146. And you can see that's not a particularly big difference in red to try to highlight where this object could come down. And you immediately realize that any of the risk that is going to come down over, say, the United States or Portugal or Spain is pretty much remote from this perspective. And you can see over on the left, there's a predicted reentry point that was in the south or in the Indian Ocean south of Sri Lanka, and gives you a good sense for where it could come down. But each of these tracks, as they walk from the east to the west, as the Earth's rotating underneath the orbit, you can see that the orbit is slowly decreasing to the point where we expect the atmospheric effects to eventually take over. And so you would expect that you could actually have a reentry anywhere along the red parts of those orbits, but we're expecting it to occur on the orbit that's shown there with the reentry south of Sri Lanka. And so it turned out, when we looked at the final results, that the reentry location was actually predicted to be south of India. So not far from the gray dot just to the right of it, that was that initial prediction. But by the time that event happened, the prediction that was being made by the people at the 18th Space Control Squadron had actually moved up over Greece. And so it didn't occur there. It occurred pretty much where we would have expected it to occur, along the section at the lowest point of the orbit. But you can see, even if we focus just on that one rev and just the section where we think the orbit was low enough that a reentry might occur, that's a fairly good swath of airspace that would be covered. Now, in this case, how much air traffic goes through there is difficult to say, but fortunately it did what we could pretty much guess it would do initially, is re-enter over water, since most of the Earth is covered by water. But that's not really the approach that we want to take with this. So there's lots of uncertainty involved with this. There's lots of technical challenges involved with this. Unfortunately, I don't know that we have a particularly good, or that I can offer a particularly good solution to how we improve these predictions. There's obviously a lot that we can try to do to better understand the drag environment before we get into the atmosphere. But things like modeling the breakups, modeling the attitude as we go through these breakups, and then actually predicting where on the ground it's going to come down can be an exceedingly difficult task, and will probably remain that way for a very long time. Now, of course, this kind of an approach where you can focus on a particular track makes the issuing of a NOTAM probably a little bit more easier than you might otherwise expect. But at least it reduces it from, it could be anywhere between 41.5 north and south latitude to something that's a bit more manageable. And so, and when we look at even that type of reentry, because the object can break apart as it's going through these various low points in the orbit, we can see that you can get a fairly good spread. And this is a similar type of reentry, a Long March 3B rocket body that reentered over Hawaii back in 2016, and you get a sense for the spread there. So even if we do figure out where in the orbit it's likely to come down, there's going to be a lot of uncertainty associated just because of those effects on the breakup and everything. So that concludes my presentation. I don't know if we're planning to do Q&A here, but if we do have questions, I'd be happy to answer them. Otherwise, we can take that later.
Dr. Kelso, thank you so much for the presentation. Appreciate it very much. I don't know if we have the ability to get questions from online, but we do encourage everyone that is listening and are interested in getting questions answered later to submit it to us, and we will provide the answers later on. Again, Dr. Kelso, thank you so much for your presentation. Appreciate it very much.
Thank you.
Thank you.